Okay, so does everybody see the exam? Okay. So you can see the exam? Yes, okay, good. Okay, so let's do the exam. So, so I'm gonna close the chat. So if you have questions, just turn on your mic and just talk. So, oh, whoops, my touch screen is off. Let me turn on my screen. Actually, I don't need to do that. Okay. So, okay. Okay, so this is the exam. Okay, so first there's true, false. So, okay, there's an m by n matrix. The number of pivots of the row echelon form is equal to the number of non-zero singular values. Okay, that's interesting. So any thoughts on how to approach that?
My first instinct would be to, well, think, is this easy to prove? And if it's not easy to prove, then you might be hitting something that is false, so you try to find a counterexample.
Good idea. That's a good general principle. So first you just search your brain for, well, is this true? And if it's true, you need to think about, you need to connect two things, pivots in the RAF and non-zero singular. So do you know, so the question is, are those equal? And it's for any rectangular matrix. So what do those quantities mean? Are they related to any other quantity that you know? What does the number of pivots in the row echelon form mean?
That's the dimension of the column space.
Yep, dimension of the column space. And that has a name. What's that called?
Rank.
It's called a rank. Okay, what about the non-zero singular values? The number of non-zero singular values. So in the SVD, how many non-zero singular values are there? If you don't remember, think about how you find the SVD.
You do A transpose A.
Yeah, you do A transpose A, and then the singular values are the non-zero eigenvalues of A transpose A, right?
Yes.
Okay. And, well, is that, I mean, how many of those are there? Okay, yeah, the rank. So somebody said this in the chat. So this is also equal to the rank. There's an easier way to think about, I mean, right now we were about to repeat the proof of the SVD, but you could, if you actually remember the properties of the SVD, this was this was one of the basic.
Can I have?
Oh, sorry. I think someone's mic is on who was ordering food. Okay, so the number of non-zero singular values. I mean, what does SVD mean? Well, it means AVI equals sigma I UI, right? And you have orthonormal bases VI and UI. And the number of non-zero singular values is exactly the number of VI for which this holds, right? And remember, the key thing is that the U1 through UK corresponding to the non-zero singular values form an orthonormal basis of the column spaces, right? So, I mean, you don't have to go through the whole proof. If you just remember the statement of the SVD, you get that these are both equal to the rank. So indeed, this is true. I'm not sure that's a good way to indicate it. Let me circle. Okay, any questions about this? Okay, let me erase this to make it a little bit cleaner. Okay, second question. If you have finite dimensional vector spaces and you have isomorphisms, two isomorphisms, one from V to W and one from W to Y, then they have to have the same dimension. Any thoughts on this? Yeah, true. Why is it true? Or what was the thought process for why it's true? You can just say it. I'm not monitoring the chat. Or
There's a transitive equality of dimension of the
Mhm.
subspace.
Yeah. So one way to view it is, well, isomorphism means it preserves dimension, right? Isomorphism preserves linear independence and span. So you have dimension of V equal to dimension of W from the first one. And then from the second one, you have dimension of W equals dimension of Y. So therefore, dimension of V equals dimension of Y. So this is also true. Any questions? Well, so now let's get to C. You have two orthonormal bases of R2. Then the change of basis matrix has the property that when you apply it to a vector, it preserves the norm squared. Okay, so how would you go about answering this question? So what's a change of coordinates matrix? So what's the important information here? These are orthonormal bases, right? That's given. And now you're wondering whether the change of coordinates matrix preserves the norm. So do you know any type of matrix that does preserve the norm? Rotation, yeah, orthogonal matrix, good. So this would be true if this matrix was orthogonal, right? So now you ask, is the change of matrix, is the change of basis matrix orthogonal? Right? So if the change of coordinates matrix was orthogonal, then you would be done. But is it? If you have two orthonormal bases and you change from one to the other, is that matrix itself orthogonal? Any ideas on how to proceed? How would you calculate this change of coordinates matrix? Does anybody know how to calculate it? Take B and C coordinates as the columns. Okay, that's the formula. So C gets B. This is B1 in C coordinates, B2 in C coordinates. Okay. So, okay, good. So now you want to check if that's an orthogonal matrix, right? What's an orthogonal matrix? It's one where the columns are orthonormal, right? So are these columns orthonormal? I'm sorry, please, if you're not talking, don't, let me just turn off everybody's mic actually. Someone is saying they don't have to be. Don't they? Well, let's calculate, right? So what's B1 and C dot B2 and C? Remember, C is an orthonormal basis, right? So what is this, right? So how do you write B1 and C? Well, so let's suppose C. So let's make an orthogonal matrix whose columns are C1 and C2, right? Then can you write this dot product in terms of this matrix U? So what are the coordinates of B1 in the C basis?
Is it B1 dot U?
Well, U is a matrix, so it's close. It's U transpose B1. Somebody said U inverse B1. That's correct, but U inverse is B transpose, is U transpose, right? So this is just this, right? And now, aha. So what? I mean, that's kind of nice, right? What property does a orthogonal matrix have? Maybe I'll write it more suggestively in this notation, right? Dot product is just the transpose of the first vector times the second vector, but now this is identity because U is orthogonal. So this is just, sorry, this is B2, so this is B1 transpose B2, which is 0. So actually, the columns are orthogonal. Are they also unit vectors? How would I figure out if the columns of the change of coordinates matrix are unit vectors? Yes, because norms are preserved. The same argument shows that if you have B1 dot in C coordinates dot B1 in C coordinates, that's B1 transpose B1, which is 1. How did I get U1 transpose B? So I use the fact that yeah, maybe I should make a better system for writing. Wait, let me expand this so I can write smaller. Okay, so how did I get U1 transpose B? Well, the way I got U1 transpose B is just the formula for coordinates, right? So B1 in C coordinates is U inverse B1, right? That's just the formula, because remember, U is a matrix whose columns are C1 and C2. But what's U inverse? It's U transpose, because it's an orthogonal matrix. Does that make sense? Okay. So that actually checks out, right? That both the orthogonality and the norms are preserved. So then this matrix, is this an orthogonal matrix? Yeah, because it has orthonormal columns, so therefore it preserves this property. So this is true. Okay. I mean, there's also a very slick proof of this, which is you can write P C gets B as P C gets E times P, or P E gets B, right? But now both of these are orthogonal because C and B are orthonormal bases. So that means a product of orthogonal matrices is also orthogonal. That's a slick matrix algebra way to do this. So usually in linear algebra, there's like a very conceptual way to do it step by step. And then there's a slick matrix algebra way to do it. No, neither is better than the other, but you know, it's a matter of taste. Any more questions about this? Okay, so let me erase this and move to the next question. Wow, okay, I guess we should go a little bit faster. Okay. So the next question is, for every non-zero vector V, there is a basis of R3 containing it. So you have some vector V in R3. The question is there some basis containing it? So how would you go about thinking about that? Do you know any way to find a basis containing a given vector?
You can just pick any two vectors, right? That are orthogonal.
Yeah. So somebody said, yeah, you can just pick any two vectors that are orthogonal to it. And there are many ways of doing this. So you could, somebody said Gram-Schmidt. Now that's a good thought, but to do Gram-Schmidt, you already need a basis, right? So not quite Gram-Schmidt, but the right idea. Take V, now choose a vector orthogonal to it. Okay. Now why can you do that? Why is there a vector orthogonal to V? A non-zero vector orthogonal to V. Why does such a vector exist? Okay, let me ask an easier question. Suppose you have V. Oh, sorry, was my internet dying? Oops. Okay. My question was, why is there a vector orthogonal to V? Why does such a W exist? Because we're in R2. We're not in R2. We're in R3. I mean, there are many ways to see this, right? So, so choose W orthogonal to V not equal to 0. Why? Many ways to see it. One is you're just trying to solve the equation W1 V1 plus W2 V2 plus W3 V3 0. That's a linear system with one equation and three variables. That's always and homogeneous. So this is always going to be consistent. That's one way to see it. Another way is the orthogonal complement of W has two dimensions. So you can choose some vector in there. And then you can repeat this now. So then you can choose some U orthogonal to both V and W. You're basically doing Gram-Schmidt, but you're choosing the vectors as you go along. You're not given a basis already. And this actually proves a stronger thing. It proves that there's an orthogonal basis containing V, which in particular is a basis. Okay. So U, V, W is an orthogonal basis. There's an easy, you don't have to use orthogonality. There's an easier thing you can do here, which is just what we did even before the first midterm, which is just choose some W not in the span of V. So just choose some vector that's not parallel to V, and then choose some U that's not in the span of V and W. And you can always do this because the span of V and W is two-dimensional and R3 is three-dimensional. So not everything is in that span. I'm not sure what's going on here. Okay. So this is anyway very true. We have two different ways of constructing a basis containing V. Any questions? Okay. Okay, if every non-zero vector V can be written as A plus B for some non-zero vectors A, B that are orthogonal. Interesting.
False.
Okay, so somebody thinks it's true, somebody thinks it's false. Why do you think it's false?
Oh, wait, I changed my mind. True.
You changed your mind, true? Okay, why do you think it's true?
If you can have an orthogonal basis of R2, and so you can write any vector in R2 as a linear combination of the two basis vectors.
Okay, but I wanted both of them to be non-zero, right? So you can have an orthogonal basis, fine.
Oh, but the dot product isn't conserved when you weight them, right?
No. My issue is, what if V is literally equal to A, right? then V is literally just equal to A.
Mhm.
But it's not equal to A plus B for A and B both not 0, right?
Oh, I see what you mean.
Somebody's saying you may need weights on A and B. Well, that's not a problem, right? I can just absorb the weights into A and B itself. I never said they have to be unit vectors, right? So somebody's asking, what about weights? Well, suppose I had a V like this, right? Then I could write V as, A dot V times A plus B dot V times B. And let's say A and B are unit vectors, right? Sure, it looks like you need weights, but now you can just take this to be A and this to be B, right? So that's fine. The weights are not a problem. So yeah, now we're getting to something. This is true for any vector except A and B itself. Yeah, why can't you just choose another basis? Exactly. That's the solution, right? So the right solution is, so this is true. And the solution is, well, if you give me a V, I'm going to choose an orthonormal basis where neither vector is parallel to B. So I'm going to choose some A here and B here. So choose orthonormal basis AB with neither parallel to V. Okay, and then when you do the expansion, you will get this, and neither will be 0. Does that make sense? You can also view this as the decomposition theorem, right? You decompose V into these two components. These are two non-zero orthogonal vectors that add up to B. Okay, so that's a slightly tricky one. It is actually true. The key is you have to choose the basis depending on the vector. Any questions? Let's move to the next one. If V is a finite dimensional vector space and some set of vectors spans V, then it contains a basis. Okay, somebody asked, what happens if V equals A? Yeah, the key is you can choose A depending on V, right? So V never has to be equal to A, right? You're wondering what if V is here and A is here, right? Well, what I'm saying is you just don't do this. You just choose a different V. So V is here, you choose an A maybe like this. You just rotate it a little and then you're not in that situation. Yeah, it's a little subtle. That's the key, right? You can choose A and B depending on V. You're maybe not used to doing that in the course, but that's somehow why this is a key question. Okay, so let's get to question F. The finite dimensional vector space and S spans V, then S contains a basis of V as a subset. True. It's true. This is true by the Goldilocks kind of theorem, right? So if it spans, if it's not linearly independent, just delete a vector if not linearly independent and repeat until linearly independent. So let's say you do this process, right? Why it doesn't change the span? Why doesn't it change the span? Why doesn't this process change the span of S?
Because the vector that you delete can be written in terms of the other vectors.
Exactly. When you delete a vector that's a linear combination of the other vectors, deleting it doesn't change the span. Okay. G. If X is a solution of AX equals B, then X is in the row space. Okay. So how would you go about that, approaching that question? What's the row space, by the way? So let's say A is M by N matrix. the row space is living in what vector space?
Rn.
Okay, so the row space is subspace of Rn. Good. Okay. So yeah, it's asking if Ax equals B, then X must be in the row space. So, okay, well, the dimension at least checks out. The first thing you should do is check if the dimension makes sense. That makes sense. X is an Rn, row space is an n vector subspace of Rn. So, okay, at least the dimension checks out. So, how would you go about approaching this? So in situations like this, draw a picture, right? So Rn and Rm, and here you have some B, and it came, and Rn is divided into two spaces, right? The row space. And what's the orthogonal complement of the row space? Null space. E came from somewhere. Now somebody said column space. That's not true. The orthogonal complement of the row space is the null space. Now the E definitely sits in the column space. That's true, and it came from somewhere, right? Ax equals B. And the question is that somewhere, does it have to be in the row space? Or maybe it came from the null space, or maybe it came from neither. So can you, I don't know, do you think this is always has to come from the row space or not?
If B is a zero vector.
Yeah, if B is zero vector, it definitely comes from the null space. That doesn't actually contradict this, because if B is zero, then X is zero, right? Okay, good. It contradicts it if the null space, I think what you mean is if B is zero and you choose a vector that's non-zero but in the null space, then it contradicts it. So you're right. So the answer is this is false. The reason it's false is if B equals zero, any X in the null space is a solution, and this may not be in the row space. In fact, won't be in the row space if non-zero. Because the row space and the null space are orthogonal complements. So any questions about that? If span of row space equals Rn, but we know X any possible because B is any possible, then okay. If span of row A. Okay, so row A is already a subspace, so you don't need to take span. Oh, you mean span of the rows? Okay. If row space is not Rn, but we know X is any possible vector in Rn because B is any possible solution, would that prove it false? Yeah, actually, yeah, that's also an interesting argument. What you're saying is that because B can be anything, right? Then as you vary B over everything in the column space, basically, if you plug in all possible values of X and Rn. No, actually, wait. No, that logic doesn't quite work. I'm sorry. So, okay, so your logic is that B is any possible vector, and you're trying to use that to conclude that X can be any possible vector, right? Yeah. Oh, yeah, that's correct. That's a really clean way of looking at it. Sorry. So here's the other solution. The claim is since B in column space of A is arbitrary, I mean, well, okay, maybe the right way to phrase this is the column space of A is the set of all AX such that X is an Rn. And it's asking about a solution. Do AX equals B for any B, right? Any B, well, which must be in the column space, otherwise there's no solution. And what you're saying is that such a solution could literally be any X in Rn. That is correct. And then if you have a matrix whose row space is not Rn, then they're not equal. That's correct. That's also a good proof. So as I said many times, there are like 10 different ways to do any of these questions, and you should find one that you're comfortable with. Any more questions? Yeah, I mean, basically what the second proof is saying is that in this picture, in here you have the column space. And if you look at all the arrows going back, if you look at all the arrows, if you look at all the vectors that map into here, it's literally everything. It may not be in the row space. Okay, good. So let's move to the next question. Actually, I really would prefer if people speak because this is being recorded. And in the recording, the chat is not visible. So actually in the future, please, I didn't realize this earlier, but please ask the question by speaking. Okay, so the next question, if W is subspace of Rn, then the standard matrix of the orthogonal projection onto W must be diagonalizable. Okay, any thoughts on how to approach that? I mean, it's relating a number of concepts, right? So one is a standard matrix of orthogonal projection, and the other is diagonalizable subspace. So first thing in any question is make sure you understand all the words. So these are the words, actually 4 words. So, I mean, okay, what does it mean to be diagonalizable?
If it's diagonalizable, then it's similar to a diagonal matrix.
Similar to diagonal? Okay, yeah. Similar to a diagonal matrix. Any other definition?
It has to have like n independent eigenvectors.
Yeah, has n linearly independent eigenvectors, right? Any other okay, so that's what it means. Now we could either directly try to go with the definition or do something a little, think for another moment. Do you know any simple condition that guarantees that a matrix is diagonalizable?
If you have n distinct eigenvalues, does it mean it's diagonalizable?
Okay, it's divided by n distinct eigenvalues. An even easier condition, actually, that doesn't always hold. Even this doesn't always hold. But there's an even easier condition. Such sometimes when you see a matrix, you just know it's diagonalizable. And what condition is that?
Is it if it's square?
Square? No, square is necessary to be diagonalizable, but square doesn't imply diagonalizable, right? Like, I mean, our favorite non-diagonalizable matrix, this is square, right? It's not diagonalizable.
If it's already diagonal?
If it's already diagonal, okay, fine. But what's the next best thing? Like, fine, if it's already diagonal, it's diagonalizable.
If it's like upper triangular, does it mean it's always diagonalizable?
No, this is not diagonalizable and it's upper triangular.
Oh, right.
If it's symmetric.
That because it is symmetric, it's orthogonally diagonalizable. So the P you get from A would actually be the orthogonal basis of A.
Good. Okay, you're on the right track. You're not exactly done, but good. The thing I was looking for, which gives the easiest solution to this question, is symmetric always implies diagonalizable, right? That's the spectral theorem. It's like, you know, a deep theorem, but that's what it says. If a matrix is symmetric, if it's equal to its transpose, it's diagonalizable. So in practice, this is the first thing you should check. Because doing this these are relatively harder, right? You need to compute the eigenvalues. Okay, so how do you write the standard matrix of an orthogonal projection? So let's say W is the span of some U1 through UK, right? What is the matrix of the projection onto W?
You just take the standard basis of Rn and then take the projection of that onto the span and then find them.
Okay, yeah, you could do that, but okay, fine. So it's the projection of E1 to the of Vn. But that's not so.
U transpose?
Yeah, exactly. So this, what you said is correct, but that's not so easy to see why it's symmetric. What really helps is that the matrix of the projection is U times U transpose, right? If U has columns equal to these vectors. And that is symmetric, right? So that's it. This is symmetric because of this formula U transpose. So it's symmetric, so it's diagonalizable. Okay, you could also do this using, so by the way, let's consider the other possible ways you could have done this. So, you know, you could have tried to do this, right? But would that have worked? Will that work in general? What are the eigenvalues of an orthogonal projection?
One and zero.
1 and 0, yeah. So then if n is bigger than 3, they're not going to be distinct, right? They're going to have either 2 1s or 2 zeros. So this can't possibly work to answer this question. There's no contradiction because that's just a sufficient condition for diagonalizable. It's not necessary. This one you could also do. You could construct n linearly independent eigenvectors. You could do that. And that's a good maybe exercise to do offline. But the easiest way is just, well, it's symmetric, so it's diagonalizable. Okay, so is that okay?
What's a standard matrix?
Standard matrix means matrix with respect to the standard basis.
Okay, thank you.
Okay, any other question about that? Okay, so let's now go to the next question. If A equals A transpose, so if A is symmetric, and P is the orthogonal projection onto the column space of A, then AP equals PA. Oh my God, I can't believe I asked you this. Okay, that's a great but quite difficult question. Anybody know how to proceed with that?
Could you take advantage of the fact that P times A still gives you A and then go from there?
Yeah. So, so you want to use, so that P times A, sorry. Oh, I'm sorry. I'm using two different annotation tools. Let me not do that. Right. Sorry. Yeah. So you want to use that P times A equals A. Now, why is that? Well, because P is the projection onto the column space, right? So if you have PAX, this is always in the column space, right? So then that equals AX for all X. Okay, good first step. So PA equals A. So we would be done if AP also equals A, right? Right? So do you think AP equals A? So far we haven't used that it's symmetric, right? We remember we're given this important piece of information. We have to use this somewhere. So yeah, do you think AP equals A? Hint, consider the previous question, or well, or whatever comes to mind. There are many
Would
ways.
it be yes, because the eigenvalues are 1 and 0?
It's yes, but it's not yes because of that reason. You can have matrices that have eigenvalues 1 and 0 and multiply them by other matrices and they still mess things up.
Can we take advantage of the fact that we know that A is symmetric and P also has to be symmetric?
Yeah, exactly. How would you take advantage of that?
What we can say is we can plug in A transpose is equal to A in PA, and then take the transpose of that, which would give us AP, and that should still equal to
Nice.
A.
Yeah. So you have the PA transpose equals A transpose because A is equal to A transpose, right? And now when you take transpose of this, you get A P transpose equals A, but P is symmetric, right? So that means AP equals A. So indeed, this is true.
How do you know P is symmetric?
We just proved that in the previous question, right? How did we prove the standard matrix of orthogonal projection is diagonalizable? We proved it's symmetric. Didn't we?
Right.
Yeah. I mean, this is the slickest way to do it. Here's a more sort of conceptual and maybe not as slick way to do it. So the first one is easy, you can get. The second one, another way to do it is observe that P is the projection onto the column space of A transpose, right? Because A is equal to A transpose, so it's a projection on the row space, right? And then you can check that this implies that AP equals P. Basically, for any vector, you apply the decomposition theorem. The part in the null space just gets killed. AP equals A, sorry. The part in the null space gets killed by A and by P, so it doesn't matter. Okay? There are multiple ways to do this question. But any questions about this? Yeah, it's kind of a tricky one.
I'm sorry, why does AP equal A?
Oh, in the second proof or the first proof?
In the second proof.
Okay, so let's do it in detail. So P is the projection onto the row space of A, right? So now we need to prove that AP equals A. So let's do that. Okay, so now let's say you have AP times some X, right? I'm going to decompose X as a component in W and a component outside W, right? Now remember, the W being the column space, sorry. Well, okay, let me write that again, actually. I really should have had a better place to write here, but okay, so let me do it carefully. So suppose X is an Rn, right? Now you can decompose X as X, let's say W plus X, where this is in the row space, and this is in which subspace? What's the orthogonal complement of the row space of A?
Null space?
Null space. Good. So now let's check that AP equals A. So what is AP X? Well, P is just going to kill the null space part, right? because of this here. And I use the symmetry to do that, right? Is that part okay?
Yes.
So now I get this is AP XW plus AP X perp, but this is just 0. And P fixes XW, right? So this is just AXW, right? But that's the same as AXW plus AX perp, because A also kills X perp, right? So that's just AX. Does that make sense?
Yes. So generally speaking, if P is the orthogonal projection onto the column space of A, AP always equals A, even if A is not symmetric?
No. P has to be the projection onto the row space of A for that.
Oh, sorry.
Right? Here we use it's a projection on the row space. The place where we use symmetry is to get from the column space to the row space.
Okay.
The symmetric matrix row space and column space are the same.
Makes sense. Thank you.
Yep. Okay, so that was that. So now let's get to the next one. If A is symmetric and all the eigenvalues are positive, then there's some B so that B squared equals A. Okay. Yeah, that's actually kind of a cool question. Any thoughts on how to proceed? What do you know about symmetric matrices and their eigenvalues?
I mean, you know that all the eigenvalues are real.
They're all real and they're all positive. What do you know about the eigenvectors?
Aren't the eigenvalues also like the squares of singular values?
Yeah, they're also squares of the singular values. That's correct. But how is A related to its eigenvalues and so on?
There's only one eigenvalue for each eigenvector. Wait, one eigenvector for each eigenvalue?
Not quite, but there is a orthonormal basis of eigenvectors, right? So what I'm looking for is you can write A as P dP transpose, where these are orthogonal, and this is diagonal with positive entries, right? Because that's what the assumption is, right? That's just the spectral theorem. Okay. So now how would you find this B so that when you square it, you get A? How do you do that with numbers? If I give you a number, how do you find another number so that when you square it, you get that number?
Square root.
Square root. Okay. So here, I'm kind of asking you to do that to the whole matrix, right? Now, what part of this could you actually take a square root of?
The D?
The D, yeah. You could take square root of each of the entries of D, right? So now just consider B equals P square root D P transpose, where this means each entry is square root. And you can do that because they're positive, right? You wouldn't be able to necessarily do that if they were negative, or you would have to use complex numbers. But if they're positive, you can do that, right? So now why does this have the desired property?
Because when you square B, you get a P transpose times P in the middle.
Exactly. So B squared is P root D, P transpose P, root D, P transpose. Another point is these are just identity because they're orthogonal. So we get P, D, P. And this is it's important they were positive, right? You couldn't do this otherwise. So this is actually a very important application of the spectral theorem, which comes up shockingly often, which is you can use it to take square roots of matrices with positive eigenvalues. So that's true. Any question? Okay. Oh wow, this had 24 points of true false. Really? Wow. Okay. Okay, K, if A is invertible and sigma is singular value of A, then 1 over sigma is singular value of A inverse. So what can you tell about the matrix already from the fact that it's invertible?
The determinant is non-zero.
The determinant is not zero. Even before that, what can you tell about its dimensions?
It's square.
It's square. Okay, so it's square. It's a singular value. So should we maybe wait? Sorry, my stylus ran out of charge. It's a singular value. So I mean, can we write the SVD? So when you see this, again, I'm asking you to relate something having to do with the inverse to the singular value, so it might be good to write the SVD, right? Where we write the full SVD. And in this case, the full and truncated SVD are actually going to be the same, right? Because how many non-zero singular values is A going to have? Let's say it's n by n.
N.
N. So these are all n by n matrices, right? Okay, good. And by the way, sigma is diagonal, and its entries are all positive, right?
I have a quick question.
Yep.
Didn't we have like a theorem or something? I might just be like misremembering, but it's like if lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. Was it something like that?
Yeah, that's correct. This is not an eigenvalue, though. This is a singular value.
But didn't we calculate sigma as like the square root of the eigenvalues?
Yes, but of what? Of A transpose A, right?
Oh, it was A transpose A.
I mean, you can go down this path and it will work, actually.
Mm-hmm.
But now you have to compare this to A inverse transpose A inverse, right?
Mm-hmm.
And the question is the inverse of this equal to this? The answer is...
Well, you know A is invertible.
Yeah.
It should be true.
It's just not true, though, right? If you literally just invert them, you get them in the wrong order.
Oh, you get them in the other order. Okay.
Yeah. So, I mean, you can still continue down this path. You can prove that these two matrices have the same eigenvalues, and then you're done. But this is a more complicated path than you need to go down for this question. So these are not equal but have same eigenvalues. You have to. That's because A, B, and BA always have the same eigenvalues if they're both square.
Mm-hmm.
Let's go down this path. I mean, you can go down this path later, but let's try to think of maybe an easier path. And it's a right instinct. It's a good instinct that yes, this was true for eigenvalues, and singular values are basically eigenvalues of A transpose A. So maybe, but there's a much easier thing you can do. So given this formula, how would you find A inverse? How do you invert a product of matrices?
You reverse their order and then invert each of the individual
So A inverse equals V sigma inverse U transpose, right? But that's just a legitimate SVD of A inverse, right? Because V and U are orthogonal. So this is SVD of A inverse. So now, what are the singular values of A inverse?
Wait, sorry, going back to the first equation, does that say A equals U sigma V transpose?
Yeah, V transpose, sorry. The U's and V's are looking too similar here, but yeah. And the second equation, you reverse the order, right? Because that's what inversion does. And because everything's orthogonal, the inverses are just transposes. So basically, I just given the SVD of A, I can calculate an SVD of A inverse basically for free, right? Just by doing this. But now, what are the singular values of A inverse?
Would it just be the reciprocals?
Yeah, just the reciprocals, right? Because the singular values live in this diagonal matrix in the middle, right? And so the diagonal matrix on the left had sigmas, which were not zero. The diagonal matrix here has 1 over sigmas. So this is true. So the easiest SVD is like, once you have the SVD, you can easily manipulate the matrix in many ways. And inversion is one of them. Squaring is not one of them, right? Computing SVD of square is not easy, unlike diagonalization. But inversion is. Any more questions about that? Okay, last question, also the hardest one. If you have two similar square matrices, every singular value of A is also a singular value of B. So this is an interesting question. It relates two notions, right? Similarity to singular values. Similarity is something having to do with, well, eigenvalues, right? And you're asking, well, if you do this, then, well, does it change the singular values? So how would you go about that? What are the simplest similar square matrices?
You look at diagonal matrices.
Yeah, look at diagonal. So when you're looking for examples, always start simple, right? So let's assume A is diagonalizable and A equals P, D, P inverse, right? That's a special case. Now, what are the singular values of a diagonal matrix?
The square root of the diagonal entries.
Well, it would be the square root of the diagonal entry squared, right? Because you'd look at D transpose D, which is D squared. So singular values equal absolute values of diagonal entries. So for diagonal matrix, the singular values are very straightforward. They're just the absolute values of diagonal entries. And what the question is asking is, now if you throw in a similarity, can it change the singular values?
Wait, sorry, why is it squared?
Well, why isn't it squared? Well, let's think about it. Singular values equal square root of eigenvalue of D transpose D, right?
Yes.
D transpose D is just D squared, right?
Oh, I see. Okay.
This is absolute value of D. I'm being very sloppy with the notation, but you understand what I'm saying. So the question is asking is, are singular values preserved under similarity? That's what it's asking, right? So do you think they are? Any thoughts on how to even proceed, or any examples you want to try? Okay, who thinks this is true? Does anybody think this is true? Nobody thinks this is true.
I think it's true.
You think it's true? Okay. Why do you think it's true?
I feel like because since A and B are similar, that means they would have like the same diagonal matrices, or like the same diagonal matrix, and then from there they have the same singular values.
So that last step. So think about how do you compute singular values of A? So what in the proof, what's the first thing you do?
For singular values, you need to find A transpose A.
A transpose A. So what's A transpose A? Well, it's P inverse transpose D, P transpose P, D, P inverse. Right? That's just what it is.
Sorry, going down a slightly different tangent. Is it possible that if we write out A is equal to U sigma V transpose and we plug it into the formula for similarity, where B is equal to like P A P inverse, and then
B,
and then knowing that P is invertible, we multiply it across and then check the conditions for it to be
an SVD?
An SVD.
Sure, let's check that. So now you have B equals, so now you multiply on both sides by P inverse and P, you get P inverse U sigma transpose P, right? So this would be an SVD if these were orthogonal, right?
But we can't assume that P is orthogonal, right?
Exactly. That's the problem, right? So if P was orthogonal, if P is orthogonal, this is true, because then this becomes identity, and then you get the diagonalization for A, which has the same, same singular values, right? Again, if P was orthogonal, these would also be orthogonal, and you would be done. But that's the issue. P may not be orthogonal. So that should make you suspicious, right? There are tons of non-orthogonal matrices I could plug in here that could, change this a lot. So in that case, do you think this is true or false?
That'd just be false, right?
Yeah, so we still don't have a proof because we need an example, right, to say it's false. But yeah, I think we've identified that for this to be true, I mean, we have actually said something quite strong. For this to be true, these would need to be orthogonal. I mean, okay, the point is we haven't actually proved that, right? We haven't proven that the SVD of, I mean, really to do it rigorously, you'd have to say, well, you'd have to solve for the singular values of B, right? I mean, we've just said B is equal to this thing. We want to say that it cannot be equal to you know, some other W sigma, let's U, or not U, let's give them different letters. So U prime sigma V prime transpose for any orthogonal. That's what you need to prove, right? We haven't actually proven that. The easier thing to do at this point is just try to come up with a numerical example that shows it's false. But I mean, maybe before doing that, let me tell you the conceptual reason why this should be false. So one of the properties of the singular value which we discussed is that the largest singular value measures how much the matrix can change the norm of a vector, right? So in particular, okay, you have this inequality. The singular values are a geometric thing. They measure how much the matrix stretches vectors. And similarity need not preserve that. Similarity is a linear algebra concept. It doesn't know about chapter 6. It doesn't know about transpose, right? It doesn't know about dot product or geometry or any of that stuff. So this might give you a hint as to how to find a matrix whose singular values get screwed up when you apply a similarity to them. So any thoughts on what's the simplest type of matrix to analyze? You could try diagonal. Do you know any other matrices? So you want to start with a matrix with singular values are very simple. Then you want to apply a similarity and just say, oh, look, they're not the same anymore. So what A would you start with?
Symmetric.
Excuse me?
Symmetric.
Symmetric, yeah, okay. Symmetric is good. What, even within that, what are the most simple symmetric matrices?
Could you just try the identity matrix?
Identity is too simple, right? If you take A equals identity and you take B equals P, identity P inverse, then it has to be equal to identity. It's actually true for identity. Okay. See, maybe what's a really simple matrix that's
Could you just do a 4x4 of like the same number? Or a 2x2 of the same number?
2x2 of the same number, okay. You mean like this?
Yeah.
Sure. Yeah, you could do that. I mean, pretty much anything you try will work. You just have to be able to calculate it. But to do something even simpler, why don't we do this? Right? That's a matrix whose singular values are 1 and 0. Right? Or another route to go with this is you could start with orthogonal matrices. What are the singular values of an orthogonal matrix, by the way? Anybody know?
Is it the norms of the columns?
Yeah, which are? So orthogonal matrix means orthonormal columns. So what are the norms of the columns? 1, yeah. U transpose U is equal to identity. So all the singular values of orthogonal matrix are equal to 1. My advice would, I mean, one, if this were true, it would mean that any matrix that's similar to an orthogonal matrix is also orthogonal. I mean, has singular values equal to 1, which actually implies it's orthogonal. Because it means all the eigenvalues of U transpose U are 1, and the only matrix whose all eigenvalues are 1 is the identity. So now this is actually a question that was on the second midterm, right? I mean, similar to a question. If you take an orthogonal matrix and apply a similarity, is it still orthogonal? So you can do, I mean, you can come up with your own favorite example. Unfortunately, to really have a proof, you need to do a little calculation somewhere. But the conceptual meaning is that similarity doesn't preserve things like norms. So that was a question on the second midterm, right? That change of coordinates does not preserve dot product. So it's another manifestation of that same fact. So this is false. So the calculation is done in the written solution. You can look at it there. Any questions? I mean, that was like the hardest question on the exam. But actually something that comes up a lot in practice. That similarity doesn't preserve singular values. Any questions? Okay, well, let's move on to section 2. I mean, okay, the hardest parts of the exam are the first 2 questions, as usual in my exam, so maybe we'll spend most of the time on that. 2A. So give an example or explain why no it doesn't exist. 2 by 3 matrix so that A transpose A and A transpose are both invertible. Anybody know how to approach this?
Choose an A that's orthogonal.
One that's orthogonal. Okay, so remember, orthogonal matrices have to be square. So do you mean, so
Sorry, I didn't see that.
So it's 2 by 3. You could still do orthonormal, I guess, rows.
Could we look at the relationship between the rank of A transpose A and A transpose compared
Yeah.
to
Good point. So what's, first of all, what's the rank of A? Well, we don't know, but can it ever be 3? Can the rank of A ever be 3?
No,
Why not?
there's only 2 rows.
There's only 2 rows. There can only be 2 pivots. So this is at most 2. And now the second fact is, well, what's the rank of A transpose A? Well, we did this many times in class. It's equal to the rank of A. Do we want to see a proof of that? We can see a proof of that. Does anybody want to see a proof of that, or is that okay?
Yeah, can we do that?
Sure. Okay, let's do a proof of that. So there are many, many proofs of this. Okay, what's the, do you want me to do a slick one or like a, okay, let me show you a really slick proof of this. So A is 2 by 3, right? So A is 2 by 3. A transpose A is, I suppose, 3 by 3, right? So in particular, by rank nullity, this is the same as saying the nullity of A transpose A is equal to the nullity of A, right? Because 3 minus the rank is the nullity in both cases. Right? Okay. Now, how do I show this? Well, there are two directions. So one is certainly, the one of these is clearly less than or equal to the other. Which one? So if X is in the null space of A, it's certainly in the null space of A transpose A. Why is that? Anybody? Yeah, because A transpose AX is also 0. So what that means is that the nullity of A trans, I mean, it just means that this set is contained in the other set, right? It means that the null space of A is contained in the null space of A transpose A. And now the interesting thing is the other direction. What if X is in the null space of A transpose A? Does that imply it's in the null space of A? Well, we're going to see that it does. There's a very slick trick here. That means A transpose AX equals 0. And now I can hit both sides, hit it by X transpose, right? But that means that norm of AX squared 0, which means AX, which means X is in the null space. So they have the same nullity, so they have the same rank. If you want, you can, is that proof okay? That's probably my favorite proof of that fact, but you can try to find other proofs if you don't like that one. There is a proof of this that doesn't use this trick with squared norm, just by tracking all the subspaces. But this is the quickest, easiest proof. So okay, so now we have.
Oh, sorry. Like on the exam, how much would we need to show a proof in order to get full credit to show this?
No, you would just. I see. So you're asking, would you have to show this fact, right?
Yeah.
Well, let's see. So I didn't prove that fact in class. Well, maybe I did. You'd have to either cite it as proven in class or explain why.
Okay, thank you.
It's best to give a sketch. Anything that's not a stated theorem in the book. I mean, anything that's not like a named thing. I mean, this is really borderline since we used this several times. Yeah, to be on the safe side, I would just explain. You don't have to maybe write the whole thing in detail, but yeah, I mean, this particular fact, since we used in class, you could say, as in the proof of SVD or something like that.
Okay, thank you.
Okay, but anyway, now once you have these facts, what's the conclusion? Can A transpose it can't be invertible, right? Yeah, exactly. So this rank is less than 2, which is strictly less than 3, so not invertible. A transpose could be invertible because that's a 2x2 matrix, but not both. Okay. Any more questions about that? Okay, let's do 2B. So you want to find a subspace, so the determinant of P and determinant of I minus P are both not 0. Any thoughts on how to proceed? So what do we know about the standard matrix of orthogonal projection? We discussed it already in the true-false, right?
Symmetric.
Symmetric. Do you know anything else about it? Invertibility, eigenvalues, etc.
p squared equals I?
P squared doesn't equal I.
Oh, sorry,
P squared equals P.
right? Yeah.
Yeah, okay, that's very useful actually. So what does that say about its eigenvalues?
Either 0 or 1.
Yep, eigenvalues are 0 or 1. And what are the eigenspaces, by the way, while we're at it? What are the vectors that satisfy Px equals x?
Would it just be all vectors in subspace W?
Yep, x and w. What are the vectors that satisfy Px equals 0?
W per.
Okay. Okay, good. So now, okay, that's a lot of information, which is more than enough to solve this question. So now you need to understand what these two conditions mean, right? So what does determinant not being 0 of a matrix mean?
Invertible.
Invertible, yeah. So both P and I minus P need to be invertible. So when is a orthogonal projection invertible? I mean, we can go down this path or we can go down this path. I don't know. What do you prefer?
Well, if it's invertible, going based off of what we've already written, that means all the eigenvalues would have to be 1, right?
Yeah, all the
Not
eigenvalues would
zero
have to be 1. Exactly. So what would the dimension of W have to be? I mean, okay, there's only one matrix with all eigenvalues equal to 1. I mean, okay, that's not true. There's only one diagonalizable matrix with all eigenvalues equal to 1.
The identity?
The identity. So if determinant of P is not 0, then P is invertible, which means P is the identity, right?
Right, which means it breaks the other condition.
It breaks the other condition. It breaks it in a horrible way, right? The other matrix is 0. So it's not only is it not invertible, it's 0. And this follows from this equation as well, because if you rewrite this, you can write it as P times 1 minus P equals 0, right? And what happens if you take determinant of this equation?
One of the determinants has to be 0.
Yeah, one of them has to be 0. You use the multiplicative property of determinant to get this, and then one of them has to be 0. Okay? Is that
a
it?
quick question?
Mm-hmm.
Why does the identity the only matrix with all eigenvalues being 1?
It's the only diagonalizable matrix with all eigenvalues being 1. Diagonalizable is important. The reason is, so I is, so let's suppose some matrix is diagonalizable. So if all eigenvalues equal to 1, that means D is equal to identity, right?
I see.
So then A is equal to P inverse, which is equal to identity.
I see. Thank you.
By the way, this is not true for non-diagonalizable matrices. Anybody have an example of a non-diagonalizable matrix with all eigenvalues equal to 1? It's a side question, but
1, 1, 0, 1.
yep. That's an upper triangular matrix. Its eigenvalues are equal to 1. And it's not the identity. So that actually proves that it must not be diagonalizable. Right? Any upper triangular matrix with ones on the diagonal that's not the identity is not diagonalizable.
Can I ask a quick question about what you wrote here, p times 1 minus p equals 0?
Yeah.
How was the determinant applied to the other side?
Oh yeah, so here I'm using the fact that determinant of AB is determinant of A, determinant of B.
Yeah. I just mean that like on the other side, what is the determinant of 0?
The determinant of 0?
Yeah, because didn't you have to apply the determinant on both sides of the equation?
Oh yeah, sorry. Determinant of 0 is 0.
Okay.
Yeah, good point. Determinant of the 0 matrix is 0. If you, yeah.
Is it p times 1 minus p, or is it p times I minus p?
Sorry, I minus p. Yeah.
Okay.
I'm just writing, yeah, sorry. It's actually p times p minus I. Well, okay, you can move the p squared to the other side. Yeah, it's fine. Okay, let's now get to this. A real 2x2 orthogonal matrix with all eigenvalues real and strictly negative. Any ideas? So what's an orthogonal matrix?
Just a negative identity matrix.
Yeah, negative identity matrix. Okay, yeah. So, I mean, there could be some thought process for coming up with this. I mean, this is actually the unique matrix with this property. But the thought process is, well, you need orthonormal columns, but then you also have to be able to compute the eigenvalues. Again, always start with diagonal matrices, right? Easy to compute the eigenvalues. So, okay, what's a diagonal matrix with orthonormal columns with negative entries minus the identity? Oh, yeah, this is a nice one. So, second order differential operator of this form with infinitely many eigenvalues, where B is an R. So you need to find the value of B such that this has infinitely many eigenvalues. By the way, what's an eigenvalue of a differential of a linear operator? What's an eigenvalue? I mean, what's an eigenvalue of a linear transformation? Like, what's the definition? This is the first interesting thing about the question. It's asking about eigenvalues of a linear transformation on an infinite dimensional space. So you can't do your correspondence principle and all that. So you have to go back to the basic principles. What's an eigenvector?
Something that changes a vector by a scalar.
Yeah, so what's the equation that it must satisfy?
Some matrix A times X is equal to lambda times X.
Yeah, but here I'm asking for eigenvalues of a linear transformation, not a matrix. So we did this at the end of chapter 5, eigenvalues and eigenvectors of linear transformations.
Like Ty.
Would be T of X.
T of Y equals?
AY.
What's A? Is A a kind of object?
It's just like a scalar, like lambda.
Okay, yeah, let's just call it lambda since that's what we're used to. And there's one more condition, right? What's that condition? To be an eigenvalue, you need to satisfy this equation, and one more thing.
Y can't be 0.
Y is not 0. So really you're asking for which values of B does this equation have infinitely many solutions? Infinitely many lambda solutions. So this equation is just y double prime plus by prime equals lambda y, right? So when does that have a non-zero solution? For which, suppose you fix B, for which lambda does that have a non-zero solution? Let me make this a little bit easier. Let me just rearrange this to make it a little more suggestive. For which lambda does that have a non-zero solution? What?
Lambda?
Which lambda?
Lambda? Non-zero?
Sure, non-zero. What's the problem with zero? If you plug in lambda equals 0, does it have a solution? Is there some problem when lambda is 0?
I have a question. Does infinitely differentiable mean that it never goes to 0, like the derivative?
Oh, no. It just means you can keep taking the derivative. The derivative always exists.
Okay, thank you.
This is the usual thing we've been looking at in our chapter on ODEs.
Would 0 still work if y was exponential?
Yeah, 0 would also work. So actually, this has a non-zero solution for all lambda. And what about b? Do you need some special value of b?
Could that just be anything too?
That can also be anything, right? So actually, by the existence and uniqueness theorem for ODE, always has a solution. So actually, the answer to this is, well, for any b, all real numbers are eigenvalues. It's a boring answer. It's not a. The whole thing was just writing the question in this form, right? You rewrite the eigenvector equation. You say, oh, it's just a second order ODE, and those always have solutions. So that's it. So the answer is no, just take b equals 0, or actually any b. Doesn't matter what b is. For all lambda, you will have an eigenvector. For all real lambda, which in particular means infinitely many. Okay. Any questions about this? The tricky part of this was just, writing down the definition of the eigenvector equation.
If y was exponential, wouldn't the only way that would be true would be if b and lambda are 0?
Well, I mean, okay, so I think maybe the important thing here is we're asking for which lambda is there a solution y, right? Now, we've thought about what the solutions of this look like, right? There are three kinds of possibilities. There are exponentials, then there are exponential times e, and then the third possibility is cosines, right? So you're asking if y was one of these, then b and lambda would have to be 0?
Yeah.
That's actually not true, right? Because This is when there are two real roots. This is when there's one real root. And this is when there are two complex roots, right? Of the auxiliary equation.
Mm-hmm.
So whether or not it's exponential is determined by whether the roots are real or not. Does that make sense?
Can you repeat that?
So these roots are the roots of this equation, r squared plus br minus lambda r equals 0, right?
Oh, yeah.
So the nature of the eigenvectors depends on the roots of that equation. So it is indeed the case that depending on what lambda is, you'll get different kind of solutions, right?
Right.
But in this question, I'm not asking you what the kind of solution is. I'm just asking you, is this any solution?
Okay, yeah.
Does that make sense?
Yeah.
Okay.
Thank you.
Yep. Any other? Okay. Let's move on to this. A second order ODE, which has among its solutions these two solutions. Anybody know how to approach this? So this is asking you to do the opposite of what we normally do. Normally we're given an equation and we need to find the solutions. Here I gave you the solutions. I want you to find the equation.
You could probably just reverse like the process.
Yeah, you just reverse the process. So out of the three cases above here, which case does this seem to fall in?
Two complex roots.
Complex roots. So these are both linear combinations of two of these exponential times trigonometric, right? What are those two functions? Well, e to the t cosine 3t. And what's the other one?
E to the t sine of 3t.
Yeah. So this is the first tricky step in the question. What I gave you wasn't, the usual basis of solutions. I gave you some linear combinations of them. So the first thing you have to observe is that, well, if these are in the solutions, then essentially by taking linear combinations, I can also get these other two. But now you can reverse engineer, right? So if these are in the kernel of this whatever appropriate operator, then what would the roots of the equation be?
One plus or minus 3i.
1 plus or minus 3i. So now, what is the auxiliary polynomial? How would you find that given these roots? So here you have alpha equals 1, beta equals 3, right? In case 3. So now what's the auxiliary polynomial given these roots?
R minus 1 plus 3i, and then R plus.
Or R minus, 1 minus 3i.
Yeah.
Okay. So then, you have to do some calculation, right? So here you just get, I guess you just get minus 2r, and now you get the product, which is like square root, or not even square root. You get 1 plus 9, so you just get 10. So then what's the equation?
Y prime minus 2y, double prime minus y prime plus 10y.
Yep. Yeah. So this is, it's just using the fact that this whole process is actually reversible. If I tell you the solutions, you can actually figure out what the equation was, which is kind of neat because you can't do that in many other kinds of equations. Okay.
And we don't have to use like any of the like, because you gave a specific coefficient that's 1, C2. We don't have to apply that at all, right?
I gave you specific what?
Coefficients, like -1 and then 1.
Oh, you mean the coefficients here?
Yeah, like they're like particular solutions. Like you found C1 and C2.
Yeah. You don't have to give that because I'm not asking you for that.
Okay, cool.
I mean, I'm just. Okay, I skipped a step, right? Technically, you have to show that these solutions are in the span of those, right?
Right.
I could have been really cruel and tricked you and given you some vectors like this, which are like linearly dependent or something. And then, but okay, you can do that, right? So, I mean, what do? I guess you maybe just subtract 3 times the second equation from the first equation.
Right. I was just wondering about that.
Yeah, no, yeah. Technically, you're right. You have to do that. Because, yeah, I kind of glossed over that, but if you take some linear combination, you get that these pure exponential times trigonometric are also solutions. So yeah, this is kind of a great question because you have to use that the solutions form a subspace so you can take linear combinations. Then you had to like do everything backwards, and yeah, I guess it involved quite a lot of knowledge. I think it was one of the hardest questions. These two questions were also among the hardest. Okay, and the last one, you want an inner product on R3. So now it doesn't have to be dot product, could be some weird thing. So that the inner product between any pair of non-zero vectors is positive. Is that possible?
Yeah, that's always possible.
Well, no, but think about what I'm saying. I'm asking you to find a product so that all vectors it's true.
Orthogonal vectors will have an inner product of 0.
Yes, but we don't. I mean, so remember, inner product is something that has 4 properties, right? So we haven't actually proven that for any inner product there are 2 orthogonal vectors. You'd have to prove that. But let's. What are the defining properties of an inner product? Well, one is the order doesn't matter. Another is that if you scale or multiply one of the vectors, it's linear. The third is it's linear under addition. And the fourth is it's always non-negative if you plug in the same vector. So now this is the interesting thing. You don't know anything else other than these 4 properties, right? So how would you use these 4 properties to prove that no such inner product exists?
I mean, for property 2, if C is a negative number.
Yep.
And you assume that V inner product W is positive, but then
exactly
for C, yeah.
Exactly. This is the key property, right? So if you have V inner product W being positive, then minus V inner product W is negative. So this is false. And you would have to, I mean, yeah, you would have to, the only way to prove that is to write down these properties and say, hey, look, there's one property here that implies that whenever you have a vector with a positive inner product, you also have a flipped one, which has a negative inner product. So they can't all possibly be positive. Does that make sense? Any question about that? Okay, so I mean, we're running out of time, but those were the hardest parts of the exam. So what I'm going to do is skip the easy questions and just do another hard one. And you can read the solutions in the written solutions. Okay, this is something we've seen in the midterm. This is easy. This is something that was very close to something on the midterm. So okay, let's vote on which question to do. So we could do maybe 4. This is kind of easy. I mean, this is basically on the midterm. It's a decomposition question. This is compute SVT. That's easy. This is find solve ODE. That's easy. This is solve initial value problem. That's easy. This is find another not inhomogeneous solution. That's also easy. Find initial value. Easy. System of ODE. Easy. Everything mechanical, really. Yeah, kind of shocking how mechanical all the rest of this was.
Yeah,
This is
like
interesting.
One that's a little more like conceptual based. That would be.
Yeah. So this is the first conceptual question at the end, I would say, and this is just compute Fourier series, also actually easy. This last one is interesting. So let's see. Yeah. Okay. The hardest hardest question was this. Similar to something on the second midterm, but not quite the same. So you have a vector space of 4x4 matrices with entry-wise addition and scalar multiplication. Okay, so many people already may have got confused. What is the dimension of this vector space? For example, that wasn't asked, but what's the dimension of M4?
16.
16. Right? You have a basis of it consisting of the matrices that only have one non-zero entry. Okay, now you have a linear transformation T of x, which is literally take x and multiply it by this matrix. So importantly, remember, this is from M4 to M4. Okay. The question is, for which values of h is this onto? What's the definition of onto? So again, this is deliberately a somewhat unfamiliar setting, so that means you have to rely on your knowledge of the definitions. So what does onto mean? Can someone state the definition of onto?
I guess the range would be all of M4.
Yeah, so the image of T is all of M4. And what that means is for every, let's call it capital B in M4, P of x equals T has a solution. Right? So this equation equals some other matrix B has solution for all B. 4. That's what you want. And you're interested for which values of H would that be true? So it's a little bit unfamiliar, right? You're used to solving a linear system where the unknown is a vector. But here I'm asking you to solve some sort of equation where the unknown is a matrix. Any ideas about how to approach this?
Maybe like row reduce?
Row reduce what?
A? I don't know.
Why though? Why would you row reduce A? Am I solving a linear system in A?
No, I guess just to see like what type of solutions you could get with A. I don't know.
Okay. Well, I mean, okay. So idea was to row reduce A. Okay, but maybe one easy thing is suppose, I mean, Is there some easy to state condition on A under which this would easily be solvable? So you're trying to solve the equation, you know, A capital X equals capital B, where these are all matrices. You want to solve for X. Is there some condition on A under which this would always have a solution?
Invertible?
Invertible. So that's certainly enough, right? The solution would just, how would you find a solution if A was invertible?
And take the inverse and find X that way.
You mean multiply on both sides, right?
Multiply both sides by
Yeah.
A inverse, right?
Yeah. So if A was invertible, then it would be onto, right? But what if A is not invertible? Could it be onto then? So here's a hint, like try to relate this to usual linear systems that you're used to. So the reason you're, I think, maybe uncomfortable is that these are matrices, right? But
would it still have a solution even if it's not invertible? Maybe like infinitely many?
that's what I'm asking you. I don't know. But here's a hint. Why don't you view B as a collection of columns? And now view the variable matrix X also as a collection of columns. So when does that have a solution?
So are you saying we should break it up and solve each?
Yeah, just break it up, right? This single matrix equation is actually just for regular linear systems, right? And you want that to have a solution for all B, right? But when does that have a solution for all B?
It can only have a solution for every B if it is invertible because it's a
Yeah.
square.
Yeah, exactly. So this has a solution for all B if and only if, for example, the first equation has a solution for all B, right? For all the equations to have a solution for all B, the first one better have a solution for all B, for all B1, right?
Mhm.
So that's if and only if A is invertible. And then, okay, you know how to check that, right, by row reduction. But the hard part of the question is realizing that it's not actually, it's in this like abstract looking setting, but it's really just asking you to solve 4 linear systems instead of 1. You could also proceed by this route, right? If it's not invertible, then it's not onto, then multiplication by A is onto, so there's some choice of B1 which cannot be achieved and so on. But you do have to zoom into the columns to apply what you knew in this question. That's the hard part. So does that make sense? So really the question is equivalent to for which H is A invertible. And that you know how to solve. But you know, most of the credit in the question was getting to that point and explaining why that's the case. If you just row reduce, there's no, you know, there are very similar problems where it doesn't make sense. Yeah, I mean, you could also do the crazy thing where you form the 16 by 16 standard matrix of this and check that that's invertible, but I wouldn't recommend it.
So,
Right,
so
so-
basically, H can't equal 1.
What? H can't equal 1, yeah. Answer is H not equal. If it's 1, then, you know, yeah, by row reduction. You basically do one row operation and then you see, you know, that it has enough pivots if it's not 1. So is that okay? Okay, so what else? I mean, These are all routine questions. Yeah, this was basically.
Is that a general principle where if a transformation is on 2, the transformation matrix is always invertible?
Well, I don't know what you mean by general. So this is a very specific type of transformation, right? Multiplication by A on one side, right? I mean, I could ask you some more complicated question. What if I ask you about this transformation? Right?
Yeah, gotcha. Yeah,
I probably won't ask you this because it's actually not that easy, but it's not, I don't know what to say about general principle. I think questions about abstract linear transformations involving matrices, like matrix spaces, should be handled on a case-by-case basis, and be very careful because all sorts of crazy things can happen.
Okay, I guess what I was asking is I thought invertibility also meant it had to be like 1-to-1.
Yeah. Oh, yeah. You could do that. Yeah. So you another line of reasoning is you could. Oh, yeah. Good. Maybe that's what you're asking. Yeah, you could do this, right? So this linear transformation T is from a vector space to itself, right? So it's onto if and only if it's 1-to-1, which is true if and only if the kernel of T is 0, right? And you could go down that path too. But at some point, you'd have to make some statement about how this relates to what you studied in the class by looking at the columns, I think.
Just to confirm, this is because the matrix A is square, right?
No, this is not because the matrix A is square. It's because the domain and codomain of the linear transformation are the same.
I see.
So this is why this question is confusing. The matrix of T in some basis, right? This is some huge 16 by 16 matrix. Right? The matrix A here is not the matrix of the linear transformation T. It's just some matrix that's being used to define the linear transformation. I mean, you can write down the matrix of the linear transformation T. Actually, if you write it down, it looks like this: A. It's a 16 by 16 matrix with a bunch of A's on the diagonal. One for each column. But I don't advise you to do this. I mean, unless you're very comfortable with that kind of thing. Which the easiest way is to directly follow the definition and observe that this matrix equation is 4 vector equations, and then it's easy. Does that make sense? What else? I mean, this is just like the Wronskian lemma. This is not very hard. This is an interesting question. I gave you a function. First, you find its Fourier series, which is something. I don't remember what it is. And now the second part of the question asks you, what's the projection of that function onto the subspace, which is the span of, sine x, cosine x, sine 2x, cosine 2x. So this is a 4-dimensional subspace S. You have some vector f. And now I'm asking you, what's the projection of f onto the subspace? What's this f hat? So what is it? So let's say I give you this expansion. How would you project that onto this subspace? So you have to go back to chapter 6. What's the formula for orthogonal projection given an orthogonal basis?
Would it just be those coefficients that you get?
Yeah, just be those coefficients. You'll have to check that, but it is literally,
It'll
A1
just be A1, okay.
plus B1 sine x plus B2 plus A2 cosine x plus B2 sine x. And this just follows, it follows from the formula, right? It's just going to be f inner product cosine x over normal cosine x squared times cosine x. Just 4 terms like this, but then wait a minute, those are exactly the terms appearing here, right? So same, chapter 6, but conceptual question that the same thing works. So yeah, I think that's it. Yeah, everything else was very straightforward on the exam. I guess it was very front loaded. Like the beginning was very hard and the rest was kind of easy. But any more questions?
Yeah, I have one more question.
Mm-hmm.
So it's not related to this exam, but I was just wondering if you could show how the column space of A perp is equal to the null space of A transpose.
Okay, yeah, let me do that on a whiteboard. So your question is, why is the column space of A perp equal to the null space of A transpose?
Yeah.
Okay. Well, the null space of A transpose, how is that related to the row space of A transpose?
They're orthogonal complements.
Yeah, so this is equal to the row space of A transpose perp. That's one of the, is that part okay?
Kinda.
Okay, so maybe let's go back to the fact why is the null space of A the orthogonal complement of the row space of A in the first place? Well, this is, let's just write it out, right? This is a set of all x so that A, which it looks like this, that's the definition of the null space, but that's just the same thing as saying x is orthogonal to, A1 and all the rows, right? But that's the same thing as being the orthogonal complement of the row space. So is that okay?
Yeah.
Okay, good. So this step is okay. And now the question is, how is this related to this?
They're equal?
Very cool, because the transpose swaps around column space. So that's it.
Oh, okay.
Yep. Anything else? Somebody wanted to talk about the 2016 exam, I guess. We have to go in a few minutes, but if anybody wants to ask, we can.
Just a quick question, generally speaking. The last exam you showed us was pretty straightforward. Are the questions going to be more complicated on the final because it is take home?
You mean, wait, you're saying that this exam was straightforward?
Well, like not obviously the first 2 questions, but definitely the last 3 or 4 questions. Will we have any questions like that, or will they all be more complicated?
No. You'll have many like that also. So, the exam will be similar to this. It might be a little harder since it's take home. It's designed to be like easy to pass, but hard to get 100 on. So it'll be similar. There'll be some quite hard questions in the beginning, and then there'll be many quite routine questions also.
Okay, thank you.
Yep. Any other question? Okay. Well, thanks a lot, and yeah, good luck on the exam.
Thank you.